Okay, let's get started. I just realized that the clock has been reset, so now the delta between real time and clock time is not as large as it used to be, so sorry for being late. I misestimate, whatever. What I'm going to talk about today is to go back and look at the zero input stability in a bit more detail, and then I'll talk about Lyapunov stability, which I think is actually a very important concept, and I'll spend some time going over how we can actually use it. It's one of the most practical approaches that we can use for proving stability of systems, especially when you talk about nonlinear systems, which is what you're going to deal with most of the time. And start with state space based control. We look at for SISO systems, single input, single output, and then I'll kind of briefly sketch multiple input, multiple output control, and look into digital control. Next lecture, that sort of ends the discussion on control theory. And then starting Monday, we'll go into a kind of an overview of some sections on probability that are important. And then after that, that'll put us into right into information theory. So there's a little bit of background on probability that's necessary. So I'll do probably 4 lectures on probability, and then the rest of it will be on information theory. Okay, to come back to this zero input stability, we're considering a LTI system, linear time invariant system, and what we want to do is to study what happens to it when we leave it alone. We just, it's got some initial excitation at time 0. Okay, at time 0 we don't know what the state is. It's not like zero input, it's not zero state. It's unknown state at time 0. What we want to show is that no matter what that initial state is, we're going to essentially dissipate the initial state down to the equilibrium state of x equals 0. And so that's what zero input stability is all about. So initial state is unknown. Or maybe I shouldn't say unknown, I guess I should say is arbitrary. It's probably a better word for it. It is known but arbitrary. And we want to basically show that we're going to get, eventually we're going to get x t goes to 0 where x is a vector. So to study zero input stability, we're going to use the state space equations, and we're going to actually use those same equations for Lyapunov and state space control. So I'm just going to put them up and leave them up in one place. So maybe I'll put it up over there so we can refer to it over here. So these are the standard state space equations. And we say x dot ax plus bu plus fw, where f is a diagonal matrix, we saw that earlier, y equals cx plus du plus e, I think ew, right? Okay. This derivative, of course, is with respect to time. So x dot is actually dx by dt, where x is a vector. So we're taking essentially it's a vector of derivatives. Okay, so the standard meaning of derivative of a vector is a vector where each element is the derivative of the corresponding element. So we have if x equals x1, x2, xn, then x dot equals dx1 by dt, dx2 by dt, etc. So in other words, we're looking at time derivatives, and I think there's some confusion about Lyapunov function. What is the derivative with respect to? With Lyapunov function, as you'll see in a bit, the trajectories are defined with respect to time. So it's always derivatives with respect to time we're talking about when looking at trajectories. Okay, but I'll come to that in just a moment. So if we have that state space equation and we want to look at zero input stability. For 0 input, we have u equals 0, and as usual, we'll basically ignore the disturbance and set w equals 0, so that the equation just becomes x dot equals ax. And that's basically just saying that the derivatives of the state variables are given by some matrix A multiplied by the current state. So we are, and if you remember, if A is diagonal, that means that each element of X, each element that describes the state evolves independent of the others. But in general, A does not have to be diagonal, it could be anything that we want. So to study zero input stability, what we're going to do is to take the Laplace transform of both sides. And so we get SXS minus X 0 equals AXS, where we've gone from the vector X, t, a function of time, to XS, which is its Laplace transform. Again, we can think of taking the Laplace transform element by element. So we have X defined in some fashion, so we can take the Laplace transform of each of these elements, and that gives us this vector XS. It's a Laplace XS. And then if you just move this to the other side, we get essentially XS equals SI minus A inverse X0. Okay, and so this is the initial state that we don't know about. Okay, it's the arbitrary initial state, and what we're saying is that given that initial state, we can find out in the Laplace domain what the state is going to be. If we are given this transform SI minus A inverse. So we basically, in the Laplace domain, we can figure out what X is going to be, and so the inverse of this is going to tell us what the xt is going to be, which is going to be the inverse Laplace transform of this over here. Okay, but instead of taking the inverse Laplace transform, it's worth looking at this particular function right here, SI minus A inverse, because this is going to show up over and over again in our analysis of the state space. And so I'm going to put a box around it. So this thing over here, SI minus A inverse X0, is essentially telling us that we can write down the value of XS, in the Laplace domain, the vector, the Laplace transform of the state, in terms of the A matrix, which is actually just the A matrix describing the system. So if we know A, we have some idea of what is going to happen to the system over time. Okay, and another way of thinking about it is that X0 is the vector of all the initial state conditions. Let's say that the system can be described using 3 state variables, x1, x2, x3. Then X0 tells us the initial values of all these 3 state variables. Okay, and we can, if we take this, what this is going to do is to essentially multiply each of those initial state variables with some description of how they're going to be dissipated. Okay, because control action is basically dissipating energy. Okay, remember that the effect of control is to move the energy from the input into all the different parts of the system and essentially get rid of it. Right. So if I had that cart and I kicked it, that's initial energy, puts it into some initial state X0. What's going to happen is that, of course, it's an uncontrolled system. That's just a normal regular system, uncontrolled system. But what's happening is that that initial energy gets dissipated as motion, it gets dissipated as friction, gets dissipated as sound. So all of these are dissipations. Okay. In some sense, what the controller is trying to do, any controller is trying to do, is that it's at equilibrium. It gets a disturbance. Whatever the difference is between the disturbance, between the desired state and the actual state, it's going to dissipate that away. It's going to get rid of that excess energy somehow. Okay, that's how we maintain control. So we want to be here. We get pushed up there. We take the error term. Think of that as being an energy term, and we're going to do control action to reduce the error, and it's the same as dissipating energy. And this understanding of what a controller is doing becomes critical when we talk about Lyapunov stability, because there we'll talk only about energy. But the other, so to go back to our canonical example of the road turning, for example, and we have the midpoint So the distance between the car, let's say the car is over here and the midpoint is over here and you want it to be over there. So this gap between where you are and where you want to be, okay, can be thought of as being some amount of energy associated with it, okay? And the controller is going to get rid of this energy. Dissipating energy doesn't mean you're getting rid of it in some sense. It can also mean that you're actually you're doing some work to get to the normal state. The energy here is sort of it's just a placeholder to keep track of the error terms, okay? So if you go back over here, what you're trying to do is that we have some initial x0. The initial x0 has got inside it some error in it, okay? Obviously, if x0 is 0, we're fine, okay? If x0 is the 0 vector, if it's equal to the 0 vector, then everything is fine because the 0 vector is equilibrium. The car is exactly where it wants to be. Its life is good. But what we're saying over here with 0 input stability is to say, okay, if I start the car way off in the side over here, the car is right on the edge of the road, and I said time 0, the car is at the edge of the road, what are you going to do? Okay? And what I want to do is to show that no matter where the car is on the road, eventually the car is going to come back to the center, okay, as long as there's no additional disturbances. So the 0 input basically says that we're not going to do anything more to it. The system is just going to essentially, continue on this path. So here by the system, I mean the control system. There's no additional disturbances, no additional control, and so I'm kind of drawing the box around the whole control system, okay. It's not just the plant. The plant, of course, without the control is just going to do whatever it's doing. The car is just going to go off the road. The control system is the one that has no additional input to it. And what is the input to it? It's a command, right? It says be here, go to the center point, go to the right side, whatever. As long as you're not changing the command, it's going to go to the center as we desire. Okay, so the U over here has to be interpreted in the context. If you look at the system over here, this is your controller, this is your plant, and this is the feedback loop. Then we have the command R coming into here, and this Y is going out of it. So this U actually refers to this one over here. That's the command that you're giving to the system saying this is where I want to be. This is the offset I want from the midpoint. So when I set that to 0, it means that I'm not going to change it anymore. I just want the initial condition where we are, and I want the controller to bring it back to 0. Okay, so this is different from, it's a different interpretation. That's why we have to be careful when we model it. Are we looking at the control system or the uncontrolled system? Here we want to look at the 0 input stability for a control system. Okay, otherwise, what's the point? I mean, it's an uncontrolled system. It's not going to be stable. It may not be stable. Who knows, right? But if it's a control system, as long as this, you're not going to change the command on it, it's going to come back to the good position. So to study this, we need to understand what is the form of SI minus A inverse. And to study this, but you say, look, what is SI minus A anyway? SI minus A is going to be the SI is just this matrix, S, S, S. It's just this very simple diagonal matrix. It is all zeros, okay? And so that's easy. And then A is some constant matrix. Because it's an LTI system, it's going to be described by some constant matrix over here. That's A. So this is just minus some A11, A12, etc. So this is some matrix over like this. So if you subtract it, what you're going to get is basically S minus A11. This is going to be minus A12, etc., right? Because those just go away. And so we have S minus A22. This is minus A23 minus A21, etc. So this is a fairly reasonable matrix. And so let's look at what's going to happen when we take the inverse. To compute the inverse, what we're going to do is we're going to write the inverse of this as 1 over the determinant of this matrix. Okay, and to do the determinant of the matrix, what do? Let's say we expand by this row over here. It's going to be S minus A11 times the determinant of this thing over here. And that's going to be S minus A22 times the determinant of this thing over here, and so on. So you can see that it's going to be a polynomial in S. Okay, it's going to be some polynomial in S over here. Okay, and so this determinant is some polynomial. Okay, is that clear? Because just for expansion of this matrix over here, just looking at it, it's clear, it's what you're going to get. We don't know what the polynomial is. It can be arbitrarily complicated, but certainly it's a polynomial. What does the numerator look like? The numerator is actually a matrix, and that matrix over here is the adjunct matrix, or it's also called, or it's the transpose of the cofactor matrix. And how do you get the cofactor matrix? What we're basically going to do is to look at the submatrices and compute the determinants inside them. But at any rate, what you're going to find is that each of these is going to be a polynomial in S as well. This is just a polynomial in S. Okay, and actually it's going to be a vector. Oh no, yeah, that's right. Right. Okay, yeah, that's right. So we're going to get this over here. So this is going to be a matrix, okay? And where we have a bunch of polynomials in S in this matrix, and this whole thing is multiplying the vector x0, which is x1, 0, x2, 0, etc. This is just the vector of the initial values of x. So we're going to take this row, multiplied with this over here, and so this whole thing is going to be divided by this polynomial, and that's going to tell us the time evolution of x1 as a function of time as a function of x0. So if you take this polynomial multiplied with this polynomial multiplied with that, etc., right, we're going to get some other polynomial in S. It's going to be divided by some other polynomial in S, and that's going to tell us the time evolution of x1. That's going to be basically x1 of S is going to be basically some polynomial in S over some polynomial in S times x0. That's the first element in capital X of S. There's going to be a ratio of polynomials multiplying x1 and 0. Similarly, we're going to have a ratio of polynomials x2 and so on and so forth. Okay? Is there any questions about that? The only part where I wave my hands, which you can probably check it out yourself, is to convince yourself that the cofactor matrix over here consists of polynomials in S as well. Okay? And from the structure of this, it'll be, if you just do the math, you'll see you'll get that. And so, from our perspective, if we want x1 of t, we have to take the inverse Laplace of this polynomial ratio and then multiply that by x1 of 0, because that's just a constant factor. And that gives us the time evolution of x1 of t. That's the first state component of t. And what do we want? We want this to go to 0. Okay. Okay, we want this to go to 0. So why would it go to 0? That is going to be true if the roots of this polynomial in the denominator, okay, the real parts of the roots are less than 0, or in the left half plane, or left hand side, right? So those roots of this determinant over here basically are going to tell us what happens, because we've seen this before. We saw exactly the same thing before. What did we see? We saw that if you have a system where the denominator is some polynomial in S, you can always rewrite this as partial fraction expansion, where we're going to take all the roots. We're going to write it as a over the first root, b over the second root, etc. And the stability criterion for the system is that essentially that the roots over here are in the left half plane, okay, or the poles of the system in the left half plane. And so, to determine the stability of the overall system, all we need to do is sort of work back to saying what are the roots of this polynomial, Si minus a, and this, of course, is nothing more than the eigenvalues of a. So the eigenvalues of a lie in the left half plane. We know that when we do all this math over here and crunch through and take this polynomial ratio and the partial fraction expansion, etc., and we take the inverse Laplace transform, we will get a system whose time evolution is going to be dissipative. We're going to get essentially exponentials going to 0. Either we're going to get a pure exponential going to 0, or we're going to get a modulated sinusoid, but that's also going to go to 0. Okay, so either way we're fine. Okay, and so we can skip this whole step. Okay, we can skip this whole step if you want to, of actually computing the partial fractions and actually computing this inverse Laplace transform, we can just go all the way back here and say, sure, if I know A, I look at the determinant Si minus A, find out where the roots are. Those are the poles. And if those poles are to the left-hand side, in the left half plane, then this system over here, x dot Ax, is going to be stable. Okay, it's going to be zero input stable. Okay, and then I'm going to make another assertion, which is by waving my hands, which is that for LTI systems under some very mild conditions, mild meaning it's almost always true, you don't really need to worry about it or rarely need to check it, and it's not even worth stating. If it's LTI stable, it will also be BI-BO stable. So if this condition holds, Si minus A inverse is, Si minus A determinant has roots in the left half plane, or more important, or equivalently, the eigenvalues of A are in the left half plane of the complex plane, then it's going to be both LTI and BI-BO stable. So which is kind of a nice thing. So if you can get our system in this form, x dot equals Ax, where A is a constant matrix, then it's a LTI system. We just looked at the eigenvalues and we're done. If it's on the left half plane, it's zero input stable and BI-BO stable, and life is good. So this basically is the way we are going to, in engineering terms, study the stability of any LTI system. And if you can get this A by doing a Taylor expansion and linearization around the operating point, we can do that too. So you say, okay, it's not linear, but my operating point is this, and in this operating point, which I'll set to be 0, in the neighborhood of the operating point, it's approximately linear because of the Taylor expansion. Then I get the A from there, and then I can just plug this in, check the eigenvalues, and basically it's going to tell you if it's stable or not. Okay, so there is sort of a plug and chug approach, which is here, or you can kind of work out the math, but it both will come to the same conclusion. Okay. Any questions about this? Okay, so I kind of rushed through this last time, and so I wanted to explain to you, but I think it's the two things which are not quite obvious from the text, I guess. One is that when I say command is 0, I really mean that input is 0, I really mean that I'm looking at the control system. I think that's not so obvious. And the second thing is that what does this really mean intuitively? This equation over here, xs equals Si minus inverse x0. Hopefully now it's clear what's going on over here. Okay, this particular, and this Si minus A turns out to be important part. Okay, so I'm going to now continue with stability, and before doing Lyapunov stability, I wanted to actually spend a few minutes talking about something which, again, it's not in the text, but it's. I just want to give you an understanding of what does it mean to have a root in the right half plane. Okay, we've talked about having roots in the left half plane as being stable, but we haven't looked at roots in the right half plane, or what does it mean to have that. Okay, must be very interesting news over there, but nevertheless, we're talking control theory here, not the news. When we have a pole in the right half plane, the system basically looks like this or like that, okay? But I mean, how can you have that? What does it mean to have that? So I'm going to now tell you an example of a system where this happens, and then you can see what's actually going on. A classic example of this is if you're in an auditorium and there's a microphone like so, and what happens is that the loudspeaker that is broadcasting the sound is being picked up by the mic again. Okay, so you get this feedback where the output is fed back into the input, and that creates this shriek. Okay, it gets really loud, and of course the system saturates, and either the loudspeaker explodes or somebody runs and turns off the loudspeaker, whatever. But I mean, what's going on is exactly this. You get this exponential increase. So this is what's called positive feedback. Okay, and in positive feedback, what's going on is that the output of the system, okay, is not what we want. Okay, maybe it is what you want, but more importantly, we have the command u is going to be essentially minus kpe. Okay, where the error, normally we have the larger the error, the more the control action. Okay, here we're actually doing the opposite thing. We have an error, and the command actually increases the error. So we have a we have a loud noise. it goes to the loudspeaker, amplified. The loudspeaker comes back as a louder noise. Now the error would be the system should be controlling it so that the volume is maintained at some optimal level, but of course a typical loudspeaker feedback system is not smart enough. Okay, if it's not smart enough, what happens is that it's going to go into this feedback loop and you get this oscillation over here. Okay, and so another way of thinking of a system where the pole is in the right half plane is that this is a system which is having positive feedback. Okay, and basically you're going to go into saturation. Okay, so that's the intuitive understanding, and you can work out the math. Of course, it's going to work out. That's what's really is going on is that we are having an error of this form. The second thing I want to talk about positive feedback is that in some cases it's very, very good to have it. Okay. Now you might say, why would you want to have positive feedback? And the reason is because we want to have some kind of a system. Let's say we want to have a system where I'm going to show on the x-axis the input, and on the y-axis I want to have the output. Okay, and what we have is, let's say when the input is negative, the output is like this, and output is, we have some kind of almost step function but not quite. And what we want is we want to have this rock solid step function like this. Okay, we want this absolute, let's say -1 and +1 and then 0, it's undefined, and then but the input is kind of this fuzzy thing. Okay, what we can do is that we can use positive feedback over here. Okay, what we'll do is that if the input is in this range over here, what will happen is it will saturate to the negative, because you see the system is not going to go to infinity, the system is going to go to saturation. So what actually happens, this is in theory, it's going to go like this. Mathematically, in practice, let's say this is the saturation level, it's going to go quickly to saturation and stay there. Similarly, in the other case, it's going to oscillate like so, and then it's going to saturate, and then oscillate, saturate, and it's going to saturate over here, basically. Okay, we're never going to exceed that because that's a physical limitation of the system. It's not going to exceed it, right? So if we set up things the right way, what will happen is that even the smallest excitation, any small error that is on the left side over here is going to, boom, saturate all the way down to this level over here, and similarly over there. So we're going to essentially convert a system which is analog, if you want, into a digital system. Okay, it's going to go into this. And that's exactly how we build things like op-amps and operational amplifiers, and we build what we call bistable systems, or memories are also like this. In memory, we want to get an input to a RAM and say, okay, here's one pulse, and it's kind of a wavy pulse, but it locks on to that value. And so if you look at it, it actually is going to be a control system which is going to have positive feedback and just saturate up all the way. Okay, because saturation means you know exactly where it's going. Okay, so yes, positive feedback can be annoying when you have a screech, but positive feedback means that we can control exactly where it's going to go. It's going to go to positive saturation or negative saturation. And so we actually design these systems to be positive feedback systems. And again, so it's an important tool to have. They say, okay, I'm going to force the system into saturation by basically taking the error term and adding more to it, kind of get into the system over here. So I'm keeping it at sort of high level, but if any of you studied oscillator design, electrical oscillator design, or latch design, or even to some extent VLSI, will recognize this as being the way we build latches, anyway, memories. So has anybody studied this at all? Or yeah, so you guys have seen this probably in your class.
That's actually used in our nervous system.
In our nervous system?
To send signals along the way.
Okay, right, because the potassium ions are going to saturate into, so yeah, the small signal between the neurons and the dendrites. When you exceed some kind of threshold, then suddenly you get this cataclysmic flood. So and the more ions there are along the nervous channel, the more ions get released. So you get this immediate saturation response, and which is why actually when you have that's why you how should I put this? That's why you cannot be. That's why stimuli are going to saturate. If you look at the sun, okay, if you look at the sun even accidentally, your retina is going to have all the potassium ions depleted from it because you have this a huge input, and so you're saturated. When you look at anything else, you're blind for a few minutes because your ions are all gone, because you have positive feedback loop built into your eye actually, which is conducting those nervous signals. So anyway, this shows up in you're right, so it's exactly a place it shows up. Okay, so that was a little bit on positive feedback, and the point being that we don't always want to have negative feedback. Sometimes we want positive feedback, and positive feedback leads to what appears to be an unstable system, but actually in this case is stable. It's stable and saturated. Okay. Any questions about this over here? Yeah. No, that's a nice thing. When you have positive feedback system, the non-linearities go away because it doesn't matter. In positive feedback, right, sure, obviously. So I think the way I would state that question is that, is saturation a good state to have, right? In some cases, if you go into saturation, it's bad. Like in the Tacoma Narrows Bridge example, you have this saturation case, and the saturation case was a bridge collapse. That's a bad state to have. If we can limit the saturation state to be some value, and moreover, we have a higher level control system that removes the stimulus and removes the saturation condition, okay, at some point when we wanted to, then we can do it. So we can say, okay, I'm now going to gate the impulse into the RAM element, and I'm going to get it into memory, and now I've taken it off. So put it into saturation. When I want to rewrite it, I know how much energy to put into it to go from a 1 to a 0, or from a 0 to a 1. So I can drive it to saturation the other direction. But the point is that the driving to saturation becomes nearly deterministic. Okay, and so we have to be careful in designing these things, but we can be careful. I just want to give you a glimpse of where positive feedback is used and what is the meaning of a pole in the right half plane. So, okay, so any other questions? Okay, let me move on to Lyapunov stability. So Lyapunov was a great Russian mathematician, and he basically studied systems from a mathematical perspective, and he came up with essentially two methods for stability analysis. And the first method is not used, and so the second method is what we'll study. That's the energy function method that we've looked at. And so, but he was looking at essentially multi-dimensional systems. That means looking at state vector descriptions, not just a single input, single output. And he wanted to kind of come up with a mathematical understanding of what it means for a system to be stable in this sense. Okay, so we have this notion of what is it to be stable in the sense of Lyapunov. Okay, and we just call it Lyapunov stable. This is a standard term. And what we are assuming over here is that we have some state vector x. It's a vector x. It's a function of t. So in the text, I just left out the t, or I guess I had it in the beginning and I took it out. But anyway, x is a function of t. So what we're talking about is that we have some description of the state, and it evolves over time. And the easiest way to understand it is, here I have a bowl, let's say, and in the bowl I have some marble which is on the edge of the bowl, and at any point in time I can describe its location in terms of a coordinate axis. So I have basically I have a x and I have a y and then I have a z, okay? And so obviously at every point in time I have a xt, yt and a zt, right? That's what I have. And so this x can be written as basically x, y, z in this case, which is the position of that point on the bowl at some point in time. So this is a function of time, okay? So we can generalize this, it can be anything. You can take a chemical process which has 20 variables, some pressure, some temperature, some fluid velocity, etc., and we can just view that as being a state vector describing it. And if you remember, for every energy storage element, we're going to have one state variable. So if you have 20 different energy storage elements, you have 20 different elements over here, and that's the state vector xt, which is basically the same thing that I have over there on the right hand side. So I'm not saying anything different, it's the same thing, except my x's go from here to